Howdy! Chapter 11, Inductance, Faraday's Law. This chapter starts with an amazing experimental result which is totally unexpected. If we have a circuit containing only a resistor in the form of a light bulb and no battery, we would not believe that the light could be turned on. From our basic equation, the integral of E dot dr around a closed path is equal to 0, or Kirchhoff's loop law, we know that no current will flow through the bulb. But if the circuit is placed in a time-varying magnetic field, the light does in fact go on. Here we have the famous experiment, a flashlight bulb connected to many loops of wire, but no battery, no power supply. Therefore, we would expect that no matter what we did, this light bulb will not go on. Here we have many coils of wire connected to an AC power supply. When I press the button, a current goes through the loops, creating a time-varying magnetic field. And as Faraday showed, when you put a circuit near a time-varying magnetic field, an amazing thing happens. The light bulb goes on, even though there is no apparent power supply. We can also show this if we take a loop. A time-varying magnetic field induces a current in the loop. There's an interaction between the current and the magnetic field. It's actually rather complicated, but it should make the loop jump. Press the button, nothing happens. A defective loop with a cut, a very large resistance. Take a regular loop, non-defective, we press the button, and the loop is launched. All of this can be explained by Faraday's law, the subject of this chapter. One can do other experiments and find that one can make the bulb turn on with a constant magnetic field if the orientation of the circuit is changed or if the size of the circuit is changed. All of these are ways in which a current is induced in the circuit, so this phenomenon is called induction. All of these experimental results can be summarized in one beautiful equation called Faraday's law. The integral of E dot dr around a closed path is equal to the negative time derivative of the magnetic flux through the path. There are two ambiguities associated with this law. When you integrate around the closed path for the left-hand side, which way do you go, clockwise or counterclockwise? For the ds vector on the right-hand side, since you are not integrating over a closed surface, which of the two anti-parallel perpendiculars to the area do you choose? There is a convention which always leads to the correct answer. Take your right hand and grab the circuit so that it is on the palm side of your hand. Your fingers now point in the direction for the path integral, and your thumb points in the direction of the ds vector. If you follow these conventions, you should always get the correct results, including the direction of any induced current. You can check to be sure the result satisfies Lenz's law. That law states that the induced current, or the induced electromotive force, must oppose the change which is causing it. Therefore, an increasing magnetic field must create a current that makes an opposing magnetic field. An increasing area must create a current such that the magnetic force on it is tending to decrease the area. You can say that whenever you try to create a current by changing the magnetic flux, the integral of B dot ds, nature works against you. There is an important feature of Faraday's law that makes calculations quite complicated. Suppose there is some external magnetic field going through a circuit, and there is a change in the magnetic flux so that a current begins to flow in the circuit. that current will itself create a magnetic field. The question is, does the magnetic field in Faraday's law refer to the external magnetic field, or do you have to include the magnetic field produced by the induced current? The answer is that you must include the induced magnetic field. In other words, the B in Faraday's law is the total magnetic field. You will note that the problems at the end of the chapter all contain the instruction to ignore the self-inductance. This is definitely an approximation and will often lead to large errors, but not ignoring self-inductance renders most problems far too difficult to solve. In the next chapter, where circuits with currents which change with time are considered, the effects of self-inductance will not be ignored. In those cases, the solution to the resulting equations can be solved. To a large extent, understanding those circuit problems is the reason you are taking this course. Understanding Faraday's law by doing the problems in this chapter will get you ready for that task. Summary. Experiments showed that the electric field created by a time-varying magnetic flux through a circuit was not conservative. In other words, the integral of E dot dr was not equal to 0. This startling result led to the general Faraday's law. The integral of E dot dr around a closed path is equal to the negative of the time derivative of the magnetic flux through the circuit. The B here is the total magnetic field, including that created by the induced current. That induced current always works against the change which is causing it. This fact, called Lenz's law, will come out of Faraday's law if the conventions for the direction of integration and the area vector are followed. Gig 'em!